In section 2.3, we're going to be looking at linear functions and slope. Now, we've been talking about functions throughout this chapter. Now we're going to focus in on one of the most important types of functions. In fact, the simplest type of functions that we work with in mathematics, and these are the linear functions. And we're going to talk about how to graph these things. We're going to talk about how to describe the graph based on different elements of the function. And one of those elements is going to be the slope of the graph. And we're going to talk about how we find the slope of a given line. Okay? So that's section 2.3. We have several essential concepts that we're going to cover in section 2.3. We're going to start off by using intercepts to graph a linear function in standard form. We're going to compute a line's slope. We're going to find a line's slope in y-intercept form from its equation. We're going to graph linear functions that are in slope-intercept form. We're going to talk about horizontal and vertical lines, and then we're going to do some word problems where we calculate the average of rates in applied situations and use slope and the y-intercept to model actual data. Let's begin by defining what we mean by a linear function. A function whose graph is a line is called a linear function. For example, f of x equals negative 2.39x plus 354.47. Now, this is a particular model equation that I pulled out of a word problem, but if I were to take this and graph it using the techniques that we've learned in the previous section, the graph would end up being a straight line. Okay. Now, how do we know it's a straight line? How can we tell by looking at a function that it's linear? Well, we're going to see two different formats that these functions tend to come in. The first is what's called the standard form for a linear equation. And here's what the standard form looks like. It's when an equation is written in this form right here. ax plus by is equal to c, where A, B, and C are numbers specific to individual problems, where the x and y are the actual variables. Now, how do I graph an equation that appears in, say, this form? Well, what I suggest doing, the easiest way to do it, is to graph using what are called the intercepts. The intercepts being where they cross the x and the y axis. So, to find the x-intercept, what you will always do is let y equal 0. Now, if you think about it, if you look at a Cartesian coordinate system, if you look at the rectangular system, and you're asking where does a particular line, if I just drew a line out here in space, right, or sorry, in the plane, where does it cross the x-axis? What is its x-intercept right there? Notice that has a height of y equals 0, right? Where it crosses the x-axis has a height of 0 because that's its up-down value, right? It is at that axis. So to find the x-intercept, we find y equals 0 and solve for x. And the opposite is true if we want to find the y-intercept. We would let x equal 0 and solve for y, because where it crosses the y-axis right there has an x-coordinate of 0, right? How high it is what we're trying to find, but the x-coordinate of that point is 0. Now, once you've done that, you have 2 points. Notice that for a straight line, all you need is 2 points to graph it, because once you have 2 points, you have your line. You know exactly where your line is and what direction it's going. Okay. Now, we also recommend finding a checkpoint, that is, identifying a third ordered pair. Pick a value for x or pick a value for y, plug it in, solve for the other variable, and make sure that that appears on the line, just as a way of checking that you got the first 2 steps done correctly. Then graph the equation by drawing a line through the 3 points. All right, look at this example right here. Let's graph by using the x and y intercepts. I'm going to set this up in a similar fashion to the way we've done it before. Let's find the y-intercept. Sorry, the x-intercept first. The x-intercept is done by setting y is equal to 0, right? So I'm going to plug in y equals 0 into this equation. Negative 2x plus 4 times 0 is equal to 12. Notice that drops out because it's 0. I can divide both sides by negative 2, and I get that x is equal to negative 6. Now to find the y-intercept, I will set x equal to 0. So if I set x equal to 0, I have negative 2 times 0. I'm just plugging it into the original equation. Plus 4y is equal to 12. That drops out because it's 0. Divide both sides by 4. And I end up with y is equal to positive 3. One last point I could find by just picking an arbitrary value for x. Say, for example, I just arbitrarily picked 2. This is just a way of checking that I got my work correct. If I plug in 2 in there, I'll have a negative 2 times 2, right, plus 4y equals 12. So negative 2 times 2 is negative 4. So add that to both sides. I end up with 4y is equal to 16. Divide both sides by 4. That means y is equal to 4. Right? 4 divides out, leaves me with 4 there. So what does that look like when I actually graph it? So let's draw my Cartesian coordinate system over here. It's going to be a little bit small because space is tight, but you can see what I'll do is I'll go down negative 6 and over 0, so actually go left negative 6, so 1, 2, 3, 4, 5, 6. There's my x-intercept, and my y-intercept is up 3, so right here. And if I went over 2, I'd be up 4. That appears to match with the straightness of that line, so there is the graph of that equation. Notice, it is sufficient to have these 2 points. The third point is just a way of checking your work. Here we have another one, very similar to the previous problem. So I'll start by drawing my t-chart. I'm going to graph the following equation. I'm going to use the intercepts to do so. So I'm going to start by setting y is equal to 0 and finding x to get the x-intercept. So that would be 3x minus 2 times 0 is equal to 6. That drops out because it's just minus 0. So divide both sides by 3, and I end up with x is equal to 2 is my x-intercept. If I set x equal to 0, I'll have 3 times 0 minus 2y is equal to 6. That drops out. Divide both sides by negative 2. I end up with y is equal to negative 3. Let's say choose a value for x. If I plug in things like 1, 2, or 3, I think I end up with fractions involved. If I choose 4, right, I'm going to get 3 times 4 minus 2y is equal to 6. 3 times 4 is 12. Subtract 12 from both sides. You end up with a minus 2y is equal to negative 6, or y is equal to positive 3. Now there's no reason why you couldn't use 1, 2, or 3 or any other number for x. Just realize if you end up with fractions, you'll want to plug them into your calculator so you can figure out exactly where that might graph on the Cartesian coordinate system. You'll have a decimal number involved in that case. But it doesn't really matter because it should fit on the line whether there's a fraction involved or not. So our first 2 points would be 2, 0. That's over 2, so it's right there. The other one is 0, negative 3, so down 3. Our next point was 4, so over 4 and up 3, which seems to match well with our line. If we draw the line through those 3 points, it's a straight line. That's what we end up with. Okay? All right. Now let's talk a little bit about properties that lines have. First of all, every line has some property known as slope. We measure the steepness of a line using the concept of slope. How steep the line is, as you say, go from left to right. The steeper it is, the higher the slope. Right? The shallower or less of an incline, less steep, we're going to say it has a lower slope or closer to zero. Okay? So slope basically compares the vertical change, the rise of a line, to the horizontal change, or what we might refer to as the run of the line. Okay? So if we think of, say, arbitrarily 2 points I've picked here on this line, right? This distance right here represents run, while this distance here represents rise. Now the ratio of rise to run is what we're going to call slope. Okay? So the slope of a line through 2 points is going to be given by the change in y, or the rise, divided by the change in x, or the run, which we can calculate using this formula. And from this point on, we're going to use the variable m to mean slope. That's just a convention that is used in algebra. M represents slope. Okay? So this is the slope formula, and that's an important formula that you're going to need to know. Okay, the slope of a line. Now, for example, here's 2 points in the plane. We got the point -7, -8, and 4, -2. We want to find the slope of a line that passes through those points. So here's what you do. Let's call this point x1, y1. We'll arbitrarily pick this to be the first point. We'll call this one the second point, so it's x2, y2. Now we have a value for each of the variables in the formula for slope. So m will be equal to y2 minus y1, so -2 minus a -8, divided by x2 minus x1, 4 minus a -7. Now minus a minus makes plus in both cases, so that's 2 plus 8 over 4 plus 7. That gives me 6 over 11. This number, 6/11, represents the slope of a line that passes through those 2 points. Now there are 4 different possibilities that we would have for a line's slope. We can get a positive value, which positive means that the rise and the run were in the same direction. That means for any 2 points, if the run is in the positive direction and the rise is also in the positive direction, or if I say I went from the second point to the first point, the rise was negative going down and the run was left. Depending on which point you go from one point to the other, if it's always the same sign, that is, you're going down and left, that means negative and negative, or you're both going positive, meaning right, and positive up, you're going to get a positive value in that fraction for slope, rise over run. The easiest way to think about it is always think of a person walking from left to right. If it's uphill, it's a positive slope. Okay? On the other hand, negative slope occurs whenever you go in the opposite sign for rise and run. Notice here the run from the first point to the second point, the run is positive because I'm going right, and the rise is negative, so I'm going down. I'd have a positive over a negative, a negative over a positive, and I would get a negative answer. But the easiest way to remember this, of course, is that if you're still walking and you're going from left to right, downhill means negative slope. Okay? So if it's negative slope, it's downhill. If it's positive slope, it's uphill. Now a zero slope would mean in the fraction rise over run, 0 occurs when the rise is 0. Okay, the run can be anything between 2 points, but the rise has to be 0, which means it's flat. A 0 slope is whenever the line is flat. Okay, and there's one other possibility. It's if in the fraction rise over run, the denominator is 0. If the denominator is 0, you have something called undefined slope, right? So that's when there's no run between the points, or you have a vertical line, right? This over here was horizontal. Okay, so uphill is positive, downhill is negative, flat is 0, vertical, you can't walk on it, so it's undefined slope. Okay, those are the 4 possibilities for the outcome of a slope problem. There is another form that the equation of a line can appear in, where you can just look at the equation and identify both the slope and the y-intercept of that line. It's something called the slope-intercept form. We had the standard form before. Now we have something called the slope-intercept form. That just means things have been rearranged, and whenever your equation is solved for y, the number in front of the x is going to be the slope, and then the number that doesn't have an x in it is the y-intercept. So for example, if I wrote down the equation y is equal to 0.968 minus 17.3, sorry, put an x in there, 0.968x minus 7.3. That's a line, and you can tell it's a line because the x's and the y's aren't multiplied together and they both have a first power. If that's the case, you always have a line. But this one is in slope-intercept form, so that tells me that the slope of the line, its steepness, is given by 0.968, and the y-intercept, where it crosses the y-axis, is negative 17.3. And by the way, here's how I know that's the y-intercept. What happens in this equation right here if x is 0? Remember, x is 0 for the y-intercept. And if x is 0, then that's not there, and so you have y as b. Right? That's why the y-intercept is b. Now what if I wrote a function down that looked like this? F of x is 3 minus 5x. Can you identify the slope and the y-intercept for this equation? Remember that we often think of the function as just another way of writing y. It's the height of the graph. It's the vertical measurement of the curve. All right, so this is almost slope-intercept form, but not quite. If I just switch the order, that is, I wrote it as minus 5x, and that's a positive streak, so plus 3. What's the slope? The slope is negative 5, right? So it's downhill, right? And the intercept, the y-intercept, is 3. Okay? Now, how do we use that information? Well, we actually have now a shortcut way to graph these functions. We don't even have to use value tables anymore if this thing is already in slope-intercept form. Let me show you. Actually, let me do one more problem before I show you how to graph using slope and y-intercept. This problem gives you an equation that's in standard form. Remember, standard form was ax plus by is equal to c, so a is 3, b here would be negative 5, and c is 7. So how do I identify the slope and the y-intercept when something's in standard form? Well, my suggestion is convert to slope intercept form. How do I do that? You solve for y. Let me show you what happens. Let's solve this equation for y. Right? This is a technique that we learned earlier in the term of solving equations for variables that have more than one variable in them. So let's try to get the y by itself. To do that, I'm going to subtract the 3x from both sides. I have 3x minus 5y is equal to 7. I'm going to subtract 3x from both sides. So I have negative 5y is equal to negative 3x plus 7. Now divide everything by -5. So we're going to divide off the -5. Now when you divide a sum by a -5, you're dividing each term by -5. So we end up with y is equal to this -3 over the -5 becomes a positive 3 over 5x. Right? I'm just writing it this over this. Negative divided by negative is positive. That's why I don't write the negatives. And then this one is going to be 7 divided by -5, or -7/5. Okay? Now from that, I can tell you what the slope and the y-intercept are. The slope is 3/5. The y-intercept is -7/5. And I did that all by just solving for y. That puts it in slope-intercept form. Okay? All right, let's talk about graphing. Graphing y is equal to mx plus b using the slope and the y-intercept. If it's in this form already, the form we are referring to as the slope-intercept form, then to graph it, what we do is we start by plotting the point on the y-axis. That is, plot the point containing the y-intercept on the y-axis. The point technically, if you write it as coordinates, is the point 0, b, right? Because it has a y-intercept of b. Second, obtain a second point using the slope m. Write m as a fraction and use rise over run starting at the point containing the y-intercept to plot this point. Now, I'll come back to this. You'll see this in the example below. So hang on if this doesn't make sense. Once you've done that, draw a line between the 2 points and you've got it. Right? Put the arrowheads at the end and you've got a line that represents the graph of that equation. Okay, so here's this example right here. We have f of x is equal to 2x plus 3. First things first, what is the slope and the y-intercept? The slope for this one is 2 and the y-intercept is 3. Okay? So without even plugging anything into the function, I can graph this thing. Let me show you. What I do is I go to this point on the y-axis. So I go up 3. Okay? Second step is to obtain a second point. That is, I'm going to write this as a fraction. Now 2 is the same thing as 2 over 1. So it's not a fraction, just put it over 1. Remember now, the 2 is rise, the 1 is run. So to get the next point, I'm going to rise 2 and run 1. Rise 2 and run 1. So up 2 because it's positive, and right 1 because it's positive. There's my second point. Up 2 over 1. There's my line right there. That's it. Done. Easy enough? Let's look at another example. Actually, I think that was easy enough. We're going to skip over the next example. Well, actually, I don't even have another example in your notes. We're ready to move on to the next one. Let's just talk about horizontal and vertical lines. You saw that there were 2 types of slope possibilities where you had a horizontal line and a vertical line. Remember that for a horizontal line, that was when the slope was equal to 0, right? So what that means for an equation is that a horizontal line is one where m is equal to 0. And so what that says is that the equation takes the form y is equal to b, where b is that y-intercept. Okay, so for example, if I had y is equal to, say, 2, right, that means that my graph would look like this. It's a horizontal line, okay, at a height equals 2. Okay, this is my line right here. A vertical line, one that has no slope, turns out it has the form x is equal to a. It's all the points where the x coordinate is a. A is called the x y-intercept in this case. All right, so if say x was equal to, I don't know, -2, then since it's x equals a number, it is a vertical line. So you'll need to be able to tell the difference between y equals a number and x equals a number. Y equals a number has a graph of a horizontal line. X equals a number has a graph whose x-intercept is at that number, so at -2, but it's vertical. So it's this line right there. Okay? I've already done a couple examples of these, but let me do these real quick. I think they're pretty simple, right? You start with your Cartesian coordinate system and want to graph y equals -4. Remember, y equals a number means it's horizontal, so that's going to be a horizontal line with y-intercept -4. So 1, 2, 3, 4. It's the line that crosses right there. Okay. Similarly, if I have x as equal to 5, sorry, that wasn't as straight as I thought it was going to be. Still, right, I go +5, 1, 2, 3, 4, 5, and draw a vertical line right there. By the way, in both these cases, I'm intending to cross exactly where that tick mark is. I just can't do it very well with my writing tablet that I'm using here. Okay. All right, so that's those types of examples. Let's do a couple of word problem application problems to make sure that we've got a good handle on what we mean by slope and intercept. In both these examples, we have the same set of instructions. They tell us that a linear function that models particular data is described. We're asked to find the slope of the model and describe what this means in terms of rate of change of the dependent variable per unit change in the independent variable. Now, in the first example, we're given the equation, we're trying to interpret it. In the second one, we're given the interpretation, and we're going to find the equation. Okay, so here's our linear function. It is y is equal to 2x plus 24. Okay, as we know, the 2 is the slope, the 24 is the y-intercept. Now we're told that this models average cost in dollars of a retail drug prescription in the United States, y, that's the average cost, x years after 1991. That's the independent variable, right? The x is the number of years after 1991. Okay, now if we have the equation, the y-intercept is the value at x equals 0. Now what is x equals 0? That's 1991 in our case, right? So this equation here tells us that the average cost of the retail drug prescription in dollars in 1991 was what? The y-intercept, 24. All right? So that's what the B tells us. Okay? So the cost in 1991 is $24. Now what does the 2 tell us? The 2 is the rate of change. Okay? That's slope is rate of change. Okay? Y with respect to x, meaning that we are going to raise the cost, the y value, $2 for every year that goes by. Okay, it's an increase by $2 every year. Okay, so here's the information provided by that equation. The slope is how fast it changes y with respect to x, and this y-intercept is the value of y when x is equal to 0. Now let us go the other direction. We're going to find the linear function in slope-intercept form using the information in the equation. Right? We're going to find the one that models the given data. We're going to describe what each variable in our model represents and then use that model to make a prediction. In 1998, there were 84 million internet users in the United States, and this number has increased at a rate of 21 million users per year since then. So let's follow the same type of model that we've done before. That is, let's let X represent the year, right? But instead of just actual year, we're going to say it's the years since the value that we actually have a starting amount for. That is since 1998. Okay, right? That means that the y-intercept, that is when x is equal to 0, is 84. Okay, where we're going to let y be the millions of internet users, because that's the information that we're given, millions of internet users, and we actually have the rate of change is also in millions of users per year. Okay, so that means my slope is 21, right? Because that's the rate of change per year, 21 million per year. Okay, so if my equation y is equal to mx plus b, that means y is equal to 21x plus 84. And there is an equation that models this situation. And we could use this to predict what's the number of, say, internet users in 2010. Okay, that would mean x is equal to what? 2010 minus 1998 is 12. So y is equal to 21 times 12 plus 84. By the way, I just picked 2010 off the top of my head. That wasn't actually in the problem, but I'm using my model to answer a question. So 21 times 12 is 252. So 252 plus 84 is 336. So that suggests that there'd be 336 million internet users by this particular model. Now that should tell you that the model is flawed and does not follow a linear trend, because there aren't that many people in the United States. But this is the correct equation. This incorrect answer here, I mean, it's correct for the model, but the fact that it's not a reasonable answer tells us that this may not be the best type of model for this particular scenario. Okay? But anyway, that's how we still set up these equations if we assume linear. And there's plenty of real-world situations out there where a linear assumption makes sense. And it may have been linear for a few years until it leveled out later on, close to the present. There's no way of knowing unless we looked at more data. Anyway, that's the end of section 2.3, linear functions and slope.